A separate question that can be asked is not whether it is a function, but once we've established that a graph is a function, we could then determine is it a linear function or a nonlinear function. Here we see some different examples. A linear function is, as the name suggests, it is a straight line. This is a quadratic function. This is an absolute value function. And this is an exponential function. At the Math 1 level, we become experts at linear functions, quadratic functions, and exponential functions, and at distinguishing between the three types and their features and their uses in the real world. So to begin, let's be really clear about what something must be to qualify as a linear function. First of all, if it's a function, I know that each x is going to have one y. Each x has one y. But there is something very specific to a linear function that sets it apart from exponential and quadratic functions. And that is this: slope is constant. The ratio of change is the same for each interval. So to restate, slope is constant for a linear function. Let's apply that when looking at these tables. In each of these tables, when I look at it, it looks like it is a function because each x only has one y. But the question here is which one of these is a linear function? So that means the slope must be constant. One thing I could do is I could literally graph the points and determine, does it form a straight line? I'm not always the best at visualizing that from just a table like this. So what I do is I measure my slope from each interval to each interval here to see, is it constant the same every time? So here, to go from -4 to -3 is +1 while going +3. So the change in y is +1, the change in x is +3. That's a slope of 1/3. To move from this point to this point, that's a slope of 1/3. +1 divided by +3. So it's looking good. To go from here to here, that change, that rise is +1, but notice this run is +2. So the slope changed. So here, from this point to this point, the slope is 1/2. Therefore, I could prove this by graphing it, but I already know this is not a straight line. It's not a linear function because the slope does not stay the same from point to point. Remember, the rule stays the same for the relationship between the x and the y. It stays the same every time. And in this case, it did not stay the same every time. Let's check B. Looks like I'm going up by 2 every time here. I see that I'm sorry, down by 2. So let me restate. I'm going -2, -2, -2. So let's see if that interval stays constant over here, which would mean the proportion stays the same. Here I'm adding 4, but here I'm adding 5, and here I'm adding 5. So that means the slope would not be constant because here I would have -2 divided by +4 for a slope of -1/2. From this point to this point and this point to this point, I would have -2/5. So slope is not constant here. That is not a linear function. Let's check C. Let's see if I have some kind of constant interval here. It looks like I'm going +2, +2, +2. So that's looking good. But remember, it's not just one side. The proportion is what matters because that's slope. It's the proportion of rise over run. So here it's +1, but then it goes +2, +2. So slope would not be the same. From here to here and here to here, that's +2 divided by +2. The slope is 1. But from here to here, between these 2 points, I would have 2 divided by 1. That slope is 2. So I'm thinking it must be D, but I would never assume that. I would always check. So let's check. Here I'm going plus 4, plus 4, plus 4. So my rise is positive 4. My change in y is positive 4. Let's see if it holds constant. Plus 2, plus 2, plus 2. So from each point to the next point, the slope stays the same. Positive 4 divided by positive 2 gives me a slope of 2. And if I were to graph this, I would see a straight line with a slope of 2. And that's how I would know that is the linear function.